Hello, and welcome to another session on data mining. Today we'll be talking about Lagrange multipliers, but we're going to take a fun approach to that. So you must have heard the children's poem, Old MacDonald had a farm. So let's say if his farm looked like this, and he had a wire of length L, of course, and he wanted to use to enclose a rectangular barn with side lengths H and W, and to ensure plenty of space for his animals, he wanted the area of the rectangle, which is A is equal to HW, the area of the rectangle, to be as large as possible. E-I-E-I-O. Sorry for the horrible poem, but this presents a very interesting case of what is called a constraint optimization problem that we can solve. Okay, so we're gonna see what steps we need to take to help old MacDonald here. So we've got a rectangle, right? That he wants. He wants all of his animals to go into this rectangular barn that he's going to make, and he wants to maximize the area of this rectangle while ensuring that the whole of the area is you can enclose that using the wire length that he has, which is L. So the area of the rectangle is, of course, A into HW, and he wants to maximize that. So the things that he can change are the height and the width of this, or the H and W, the side lengths of this rectangle. However, as I said earlier, he wants to ensure that the perimeter of this rectangle over here, let me turn on my pen here. Let's use green because it's a farm. So let's say we've got uh, this as the parameter over here, right? Oops, wrong place. So the whole of the perimeter of this rectangle, okay, horrible drawing, but you get the idea. That must not exceed the length of the wire that he has. So because the perimeter of this rectangle is 2 times W, because there are 2 W sides and 2 H sides, so that means that what he wants to ensure that is that 2H plus W is equal to L. Okay, and he wants to maximize the area, which is the product of H and W, such that now that is a constraint, and we've got a single constraint over here, which says the perimeter of the rectangle should equal the length of the wire that he has. Okay, so this is a constraint optimization problem. We know how to solve optimization problems, right? We can take the derivative of the objective function A in this case, or area, and we can take the derivative with respect to the decision variables, which are height and width, or H and W in this case. And then we can substitute that equal to 0, or if it's a more complicated function, we can use gradient descent to optimize it. But it's the constraint that is causing us a problem here, because we don't know how to apply gradient descent when we have a constraint, right? Fortunately, this problem was thought about and solved by uh, a person named Lagrange. And what he proposes is a set of series of steps that you can take called the Lagrange multiplier method that converts this optimization problem, or this constrained optimization problem, into an unconstrained optimization problem. Okay, and we are going to follow those steps, and we are going to convert this constrained optimization problem into an unconstrained one, so that we can solve it using, let's say, gradient descent, or taking the derivative of the objective function and substituting it equal to 0. The steps that you need to take, given a constraint optimization problem, you first need to express the constraint that you have in the form of this function. So let's say if x are the variable, are the decision variables, then the constraint needs to be expressed as in the following way. So it's essentially a rewrite of the same constraint. We just need to make sure that the right hand side is 0. So this is going to be equal to g of h and w. So our decision variables are h and w instead of x. So that's why we've got this. Now, once we have expressed this constraint in this form, the next step we need to do is we need to introduce a multiplier, or another variable. So the original number of variables in this decision in this problem is only h and w. So there are 2 variables that we can optimize over. But what this method does is that, or requires, is that we introduce another or an additional variable called a Lagrange multiplier. Typically, it's denoted by alpha 1 or alpha 2 or alpha if there is only a single constraint, and that's what we're going to do. And once you have that, you can change the objective function and rewrite it in the following way. So you have your original objective function, which is a, which is equal to hw, and that is the original objective function right here. And then what you need to do is you need to just modify the objective function by subtracting this alpha times the g of x of the constraint, which is the left-hand side of our constraint, which comes out to be 2 times h plus w minus L. And there's a proof which we'll, of course, not cover, but what says that if we solve this optimization problem, which is now an unconstrained optimization problem in 3 variables rather than having a constrained optimization problem in 2 variables. If we are able to solve this, then it will solve the original problem that we have over here. So let's try that. Let's take the derivative. So I hope that the first thing I want to make sure is that if you want to pause the video and make sure that you understand the steps of how we use these steps to convert this constrained optimization problem into an unconstrained optimization problem mentioned over here. So please go ahead and do that. It's really easy. You've got the original objective function hw over here, and then we subtract from it alpha times the constraint, the left-hand side of the constraint, which is g of x, or in this case 2h plus w minus L. Okay, and then what we do is we take the derivative of this with respect to h, and that of course comes out to be w minus alpha times 2. Okay, so, or we can say w minus 2 alpha. Similarly, you can take the derivative of this with respect to w, and that is going to come out to be h minus 2 times alpha. Okay, and now you also need, because there are 3 variables, you also need to take the derivative of this objective function, this modified objective function, which is called the Lagrangian. And you can take the derivative of it with respect to alpha, which comes out to be 2 times h plus w minus L, and we substitute each one of them equal to 0. Okay, and once we do that, we see that we get the following values of w and h, wh and alpha. So w is 2 times alpha, which is coincidentally the same thing as h is equal. So h is also equal to 2 alpha. So I write it h is equal to w is equal to 2 alpha. And then we have got an additional equation over here, which says that 2 times h plus w is equal to L, which is the same constraint that we originally started with. Now, it's really straightforward to see that the height and the width of this rectangle that we are trying to make is equal, and both of them are equal, and they're equal to 2 times alpha. And what that means is that the rectangle that he wants to make, or MacDonald wants to make, to maximize the area such that the perimeter is of a certain length L, is going to be a square. So a rectangle with equal sides is of course a square. So we know that this is going to be a square. Okay, and then and we can work out the lengths of each side of the square by simply solving these 2 equations. So if we substitute this over here, then what we get is we get 2 times 2 alpha plus 2 alpha equal to L, or what this implies is alpha is equal to L by 8. And what that means is that h is equal to w is equal to L by 4. So the rectangle that he would make is going to be a square if he wants to use all his wire length, and each side of this square is going to be of side length L by 4. And if you see that this is going to be the total perimeter of this square is going to be equal to L, and that is the rectangle with the maximum area. So all his animals would be happy. This is the method of Lagrange multipliers. I hope this simple example would help you understand this method, because we are going to use this method in a number of other machine learning problems down the road. Thank you.